Welcome back to the Deep Dive. Our mission today is to unpack a massive, really massive and recent shift in how applications are built.
It's a change that's so fundamental, it's really questioning decades of software engineering tradition.
Exactly. We're looking at AI code generation, specifically where we are in late 2025, and how it has completely redefined the structure of applications. We're moving away from, all that complexity of traditional architecture.
To a place of, well, astonishing simplicity.
And that's the core conflict, right? That's what we see in the source material.
It really is. I mean, for anyone who's been tracking the capabilities of these state-of-the-art models, whether you're talking about the big foundational ones like open code or Google's anti-gravity.
Which is really specialized in system orchestration and these agent models we'll get into.
Right. Or even the powerful Gemini series. The ability of these AIs to generate highly functional, incredibly complex code is, well, it's already a given. They can build enterprise-level applications.
But the real insight today, the thing that really caught our eye in the source material, it isn't just how much code they can generate.
No.
It's how little infrastructure they ultimately need to achieve the exact same really complicated result.
Precisely. And we've got sources detailing two distinct AI-generated applications. They do the identical thing, a sophisticated task of generating multimedia content.
Okay.
But one looks like, it looks like a traditional software engineer's magnum opus, a meticulously organized, multi-stack symphony of services and databases.
Another one.
The other one is almost criminally simple. It's boiled down to a single Python script.
Wow. So our mission today is clear.
Mm-hmm.
We are hunting for that aha moment in the transition. We're moving from a world where application architecture required massive specialized planning.
The kind of thing that takes years of experience to master.
Right. To one where a simple high-level instruction just handles all that complexity under the hood. It's making all these traditional programming concerns feel, well, irrelevant.
And the speed of this shift is just breathtaking. That's what we really need to illuminate for you, the listener.
Okay, so let's start by setting the stage with that first example. The source calls it the Code Venture application.
Right. This is the one that demonstrates, let's call it, maximum architectural debt.
Maximum debt, I like that. So it's a highly specialized workflow manager, and it's focused entirely on content generation.
And crucially, a human provided the natural language instructions, the high-level goals.
But the actual code?
The AI generated it all, down to the last database schema definition. The human developer, they manually touched almost none of it.
And we really need to underscore how difficult this task was. I mean, the AI wasn't asked to build a simple to-do list.
Not at all. This application manages a dynamic, multi-stage workflow. It's designed to turn these vague, simple text ideas, just a raw concept, really into a professional, finished, highly customized video asset.
Something you could actually post on social media or publish.
Exactly.
Okay, so let's walk through the full 8 steps of that process, because I think it really illustrates the immense architectural demands that follow. It starts with a simple text idea, right? Something vague like, the ocean makes me feel calm.
Right. So step 1. The AI first has to take that vague instruction and use its own inference capabilities to expand it into something specific, detailed, and high fidelity.
A proper prompt.
A proper prompt. And this detailed prompt is the secret sauce. It's necessary because it sets the precise visual and thematic stage for all the high-quality, resource-intensive steps that come after.
Okay, so you have this detailed prompt locked in. Then step 2. They use that output to generate a high-quality static image.
And that image acts as the visual seed for the entire sequence. Then step 3. Based on that static image and the detailed prompt, the system generates a motion video.
So it's inferring movement.
It's inferring movement, temporal changes, a narrative flow, all based on that static input and its context.
This is where that resource constraint becomes so critical, isn't it?
Absolutely. This kind of content generation often relies on specialized large inference models that are running locally. We're talking services like FramePack for advanced video composition or Focus for high-fidelity image generation.
These are massive, power-hungry models. They require gigabytes and gigabytes of VRAM.
It too. And if you're running this on your own local machine, even a really high-end desktop in late 2025, that memory requirement is the absolute centerpiece of the complexity we're about to get into.
You just can't run all 8 steps at the same time.
No way. You'd crash the system. So moving on through the workflow, step 4. Audio is generated and integrated into the video. This could be music, narration, sound effects, all tailored to that detailed prompt.
And then step 5 is kind of a meta step, right?
It is. The application analyzes the video and the prompt to summarize its core emotional or thematic meaning. It extracts a key text quote or poem or some profound message. It's literally seeking meaning from the content it just generated.
And then we shift gears visually. Step 6 takes that original image from Step 2, slaps a heavy blur filter on it, and uses that as a background for the text quote.
Which ensures the text is legible, it stands out, it's visually appealing.
Step 7. A second video clip is generated, and this one specifically showcases that text overlay, maybe with some subtle motion.
And then finally, step 8. The two completed videos, the original content video and that concluding message video, are concatenated or merged seamlessly into the final product.
I mean, that is genuinely enterprise-level functionality.
It really is. You've got multiple modalities: text, image, audio, video. You've got multiple large language models, multiple dedicated local services, and really complex data handoffs between all of them.
But the app structure, the thing the AI built to support all this, it looks exactly like the most complex traditional software architecture. It required this incredibly complex structure just to manage those moving parts. Why? Why did the AI choose that path?
Well, it chose that path because when it was instructed to build a robust, scalable application that supports all major platforms and handles resource management, the only pattern it recognized was the traditional software stack.
So let's look at those components. The front end was a Flutter application.
Right. And Flutter is great for providing native support across Android, Windows, Linux, iOS, all at once.
But that choice, it dictates a certain kind of architectural commitment, doesn't it?
It does. The Flutter application used the provider-consumer pattern for state management. Now, for those who aren't familiar, state management is basically how you make sure that when a piece of data changes, like the name of a workflow, all the parts of the UI that rely on that data update instantly.
And the provider-consumer pattern, I mean, it's robust, but it requires a massive amount of boilerplate code.
The huge amount. It's disciplined, it's scalable, it prevents errors like prop drilling, where you have to manually pass data down through 5 layers of widgets, but it demands a really rigid structure.
So the AI generated pages and pages of code just for this.
Pages, just setting up this disciplined data flow, handling desktop screens, mobile screens, all to support the state changes from things like dragging and dropping nodes on a canvas. It was architectural mimicry of human tradition.
And the backend supporting all of this was a Go application.
Yeah, Go or Golang. It's a common choice for high-performance concurrent backend services. The AI chose it to define all the business logic and endpoints because it needed speed and stability for the core orchestration.
And it went beyond just a basic API structure.
Oh, yeah. The application required sophisticated features, drag-and-drop workflow design, saving and loading of node templates, and critically, a queue manager.
A queue manager for handling failed items that needed to be logged and reprocessed.
Exact.
The queue manager itself is a huge hint about the complexity here. I mean, why can't the process just run? Why do you need a complex queue manager built into the core architecture?
Because of that local resource constraint we mentioned, the context of late 2025, where these big inference models like FramePack and Focus are running on the user's local machine.
So the workflow had to be sequential. It couldn't be parallel.
It had to be. The services are resource hogs. To run step 3, the video generation, you might need 12 gigabytes of VRAM. If step 2, the image generation, is still using 8 gigs of system RAM, you crash.
So the application architecture had to physically mirror that resource reality. It had to know about the hardware limitations.
Exactly. Services must be stopped, unloaded from memory, and then restarted or reloaded on demand for the next step. Now, this severely reduces the speed.
Of course.
Because you're constantly loading and unloading these massive models into memory, which can take, 10 to 30 seconds per step. But it was the only practical way to conserve local memory and run that entire 8-step sequence reliably from end to end.
So the AI, acting as a traditional software architect, built a complex system to manage a difficult physical constraint. So let me ask you this then. The functionality is brilliant. The AI wrote all the code for this multi-platform beast. But the underlying application architecture needed to support it looks precisely like the applications we were meticulously handcrafting 10 years ago. It feels like the AI was shackled by the concept of best practices.
That's the critical observation right there. It was complex for necessity's sake, but that necessity was defined by the existing defined patterns of how human software handles resource constraints and state persistence.
It just flawlessly executed the traditional complex stack.
It did. It showed off its ability to build an enterprise-level monolith. but its adherence to that monolith, that rigid separation of front-end, back-end, and database, that was the problem.
Okay, so let's get into the weeds of that complexity.
Yeah, let's delve into the guts of this thing. What's so fascinating here is that the AI didn't choose to abstract the infrastructure away. It meticulously recreated it, detail by painful detail.
So it built a stack that a human team of, what, 10 developers would have been proud of?
Proud of, yes, but which would also take them 6 months to maintain.
Let's look at that Go backend again. This application had to be rock solid in defining the business rules.
Absolutely. The Go application defined all the necessary endpoints and the database models. Every single user interaction, creating a workflow, getting a list of defined workflows, updating a workflow definition, it was a standardized API call.
And that call gets routed through a specific endpoint, which calls a specific service function.
Right. It maintains modularity, which is traditional best practice, but it adds layers and layers of necessary boilerplate code.
And all those models and services, they relied on a foundational database structure. The source specifies a robust PostgreSQL database.
Correct. And the PostgreSQL schema was extensive. It wasn't just storing simple user data, it was defining the structure and the state of the entire application.
So you see tables for WeFlows, nodes, edges, services.
Execution results, node templates, providers, and a queue for managing failed or pending tasks. This is the definition of relational database modeling applied to a dynamic software process.
I want to circle back to the structure of the nodes and edges tables. The source material notes, they weren't stored as traditional SQL data types. They were massive JSON objects inside the columns.
And that's a key architectural compromise. It's often known as document storage within a relational context. Workflows are highly dynamic, you know. A node for generate image might suddenly need new properties if you introduce a new AI model like a style transfer parameter.
And if you used rigid SQL columns for every single property.
Every time you updated the workflow definition, you'd have to perform a costly, risky schema migration. You have to stop the entire application.
So storing them as JSON objects, what you call databaseception, data inside of data. That was the AI's way of ensuring flexibility.
Absolutely. Storing them as JSON allows for fast serialization and deserialization. The data structure can grow dynamically without requiring those constant, painful database alterations.
But flexibility comes at a cost.
It does. It makes querying complex. You lose the rigid integrity checks of SQL, and every time the application runs, that Go backend has to take this raw JSON blob and deserialize it back into a usable structure, making sure all the necessary fields are present and valid.
So it adds execution overhead.
It adds overhead, exactly.
This complexity is already mounting, but I think the single most telling piece of architectural debt is housed in that services table.
I agree completely.
This table, in essence, it embodies the failure of this V1.0 approach to abstract away the hardware constraints.
100%. That services table was critical for runtime service management because of the resource constraint. The database had to track everything about the local models. The service name, the shell script used to start it, the URL, the port it occupied.
It was the AI's version of a sysadmin manual, just stored in SQL.
It was. But the column that defines the entire V1.0 complexity model, the one that tells the story of this forced rigidity,
is the stop services column.
That's the one. The stop services column was a literal list defined within the database that explicitly indicated which other resource-intensive services must be stopped and killed before the current service could run.
So this is not high-level abstract execution logic. This is physical, manual resource negotiation defined in a data structure.
It is. The database, which is supposed to manage persistent data, is literally acting as a task scheduler for local memory allocation. It's having to read a whiteboard list that says, okay, if I want to run the video merger, I must first ensure the image generator process is dead.
That level of manual process negotiation managed by the database is staggering, and it's terribly brittle.
It's the definition of architectural debt. The AI generated a solution that perfectly solved the constraint. It ensures the system doesn't crash from out-of-memory errors, but the method it used is cumbersome and rigid.
So if you wanted to add a new model...
If you wanted to add a new model, you wouldn't just update the Go business logic. You'd have to update the database schema definition, potentially modify the shell scripts, and definitely update that stop services list for every other model that might conflict with it.
It makes maintenance an absolute nightmare.
It does. And that tracking continued with execution. The execution results were also stored as JSON values, ensuring full reproducibility.
Okay, so that was the upside. You could always go back and see every intermediate step.
Right. The raw image, the initial video, the audio track, the final quote all, because the database held those massive binary results serialized as JSON strings. But again, it's managing complexity with more complexity.
And now let's tie this back to the user interface. The Flutter application, it needed mirror models of those complex Go backend models to manage its own internal state.
Yes. The front end had to understand every schema, every nested JSON object, and every possible result type. This is model duplication. It's a major pain point in traditional architecture.
Because if the backend team updates the workflow model in Go,
The front-end team has to manually update the mirror workflow model in Flutter. This introduces bugs, synchronization headaches, and it just slows down development.
and the Flutter app used a factory pattern for services, ensuring every provider implementation derived from a virtual method called execute node. It's all highly structured, object-oriented design, really intended for massive teams.
So the architecture demanded model duplication, complex class hierarchy management, state management overhead, API endpoint definition, database schema control, and resource scheduling via a database table.
So the verdict on V1.0 is that the AI generated a perfect enterprise-level application demonstrating sky-high code capability.
But it was an incredibly smart answer to a 20-year-old question about monolithic architecture. The resource reality forced a complex architecture, and the AI didn't abstract the infrastructure. It codified it perfectly. It just didn't realize the question, the fundamental premise of application building, was about to change entirely.
Okay, here's where it gets really interesting. This is where the paradigm just flips entirely. We moved to the second application called the Content Manager, and this one was generated by Google's anti-gravity model.
And it performs the exact same workflow as CodeVenture.
The exact same thing. Idea to merged video, the image generation, quote, extraction, audio concatenation, all of it.
All of it. The objective is identical, and yet the sheer structural simplicity is startling. The objective idea to video content is inherently simple. The new paradigm focuses on making the development and execution process match the elegance of the goal.
So the complexity of the task remains, but the complexity of the architecture just vanishes.
Completely vanishes.
So introduce it to this simple application. What technology replaced that multi-stack Flutter Go PostgreSQL beast?
It was a single, simple Python application called main.py.
Wait, I have to stop you there. A single Python script replaced an entire application architecture.
Yep.
No dedicated database.
Right.
No separate backend. No formal service layers.
Gone. All of it. All the architectural commitment we just spent the last, 10 minutes detailing, the specific abstraction of database tables, the synchronization of models across front and back end, the Go server endpoints, all eliminated.
Okay, if there's no database, how does it manage state? Or queues? Or results?
It handles execution by recording results in simple, organized sessions. These sessions are just folders on the file system named by date and time.
So it's just using the file system for persistence.
Exactly. Inside that folder, it tracks every necessary intermediate file, the image, the first video, the quote, the final merged video, and it logs performance metadata, start time, end time, duration for each step, which specific model was used, no enterprise database schema needed.
That seems almost primitive, but incredibly efficient for this specific task.
The complexity is handled by configuration, right? Like quality profiles.
Right, but the actual execution logic must be hidden somewhere. And that brings us to the core of this V2.0 model, the power of the prompt, or what the sources call the Agent's Manifesto.
The Agent's Manifesto. The entire workflow, all the sequential logic, the goals, the constraints, it's all defined in a single high-level prompt. That prompt acts as the application's constitution, its self-written documentation, and its full execution plan all in one.
Can you share what those prompt directives look like? I mean, do they look like code?
Not at all. They are purely natural language instructions that set the context, the tone, and the procedure.
So things like,
You are a creative content creator responsible for deep philosophical short-form videos, or generate 3 unique stories based on this vague starting idea, or even follow these specific guidelines for prompts and videos, ensuring high color contrast and a subtle motion blur.
and the execution plan is just listed out.
In plain text.
Yep.
1, create brief title folder. 2, generate image. 3, generate video. 4, extract quote. 5, merge all assets.
So that one paragraph long prompt encapsulates the purpose of thousands of lines of Go and Flutter code, the entire PostgreSQL schema, and all those resource management rules from V1.0.
It's abstraction at its purest. And the mechanism running this is the agent itself. The application uses a generic agent class, which is really just a robust Python wrapper around a continuous self-aware Gemini Flash 3.0 chat session.
So the AI in V2.0 isn't generating a fixed compiled application. It's running an orchestrated conversation with itself and its environment.
That's a perfect way to put it.
But I have to challenge this. How does a chat session generate an image or merge a video? That requires executing code, managing local dependencies, making API calls to those resource-heavy models like FramePack.
And this is the next revolutionary layer, the shift to tools, not code. The agent initiates the chat, it reads the manifesto prompt, and it determines the necessary actions. But when it needs to execute a heavy-lifting step-like image generation or video merging, it uses specific, predefined Python functions.
And those functions were automatically generated by anti-gravity Gemini during the agent's creation process.
Exactly. And these functions are presented to the chat model as tools or skills.
So the agent's response to the prompt isn't a new line of source code.
No, it's a command. It's instructing the agent's runtime environment to call one of its available tools with specific parameters that it derived from the context. For instance, the agent reasons, okay, the prompt demands a high-quality image, therefore I must invoke the generative image tool with the detailed prompt I just created.
So the complexity of managing specific APIs, handling data serialization, dealing with local dependencies, it's now all contained entirely within that auto-generated modular Python tool definition.
Right. The core application, that simple main.py file, doesn't need to know anything about the API structure or the exact data types beyond the high-level input required for the tool. The agent figures out the rest.
Which means the programmer only interacts with the manifesto, the prompt. The agent handles the complex function calls, the argument structuring, the error handling. All of it is inside those tool wrappers.
Yes.
Okay, now this is the vital connection back to Section 2. We established that V1.0 needed that complex services table in PostgreSQL with a manual stop services column just to handle the constrained local environment and prevent system crashes. How does the simple V2.0 agent solve that same complex resource-constrained flow without any of that defined structure?
And this is the true genius of the agent model. Its ability to handle complexity liquidity. It didn't need the database architecture because it generated its own dynamic service manager functionality.
Dynamic.
Yes. The agent knew, based on its manifest and its available tools, that the environment was resource limited. So as part of its own execution logic, not as a defined database table, it generated simple Python code that includes functions to check if a port is in use.
Okay.
Use the operating system's kill command to take down old processes, wait for a service health check by pinging an endpoint, and then use the standard Python requests library to make the necessary API calls to locally hosted services like FramePack.
So it intelligently orchestrated the exact same complex resource flow starting models, stopping previous models, checking health, managing the sequential flow, but it handled it all through prompt execution logic and dynamically generated helper functions.
That's it. It's like the traffic controller analogy we discussed before. V1.0 was a team of engineers building a physical rail switching yard.
And V2.0 is just an AI telling the driverless trains, get to destination C, and the agent figures out the best path, the stopping protocols, and the resource allocation on the fly.
The architecture moved from being fixed and defined in rigid SQL tables and Go models and Flutter structures to being liquid and executed on the fly by the agent's interpretation of the natural language prompt.
The complexity wasn't removed. It was just abstracted one layer up, making the underlying application structure trivial.
It demonstrated that infrastructure is just one more piece of logic that can be written, managed, and changed instantly by the AI itself.
And the beauty of that is if the resource constraint changed, say you move to a powerful cloud server with infinite parallelization, you don't rewrite the code.
You just change the manifesto prompt to remove the constraint. You just say, this is a high-resource environment, execute steps 1 through 7 in parallel.
The code remains disposable, and the architecture becomes situational.
Exactly.
So if we connect this pivot from the enterprise-level complexity of V1.0 to this agent-driven simplicity of V2.0 to the bigger picture, this fundamentally changes, well, everything. The job description of the programmer, the value chain of software, the relevance of their current tools.
It does. And the first major implication, and maybe the most difficult one for career programmers to internalize is what the source is termed the disposable code.
Disposable code.
Absolutely. I mean, think about the massive time investment we place in choosing a language, a framework, a library. In V2.0, all of that becomes almost irrelevant, or as the sources put it, trivial.
Because the code artifact itself is now disposable.
Yeah.
The high-level specification, the prompt, the manifesto can just generate a new compliant version instantly.
Exactly. This means if the preferred language shifts from Python to something new next year, or if the underlying cloud platform releases a whole new set of optimized APIs, the human developer doesn't need to engage in that painful multi-year migration process that characterizes large legacy software.
They just rerun the V2.0 manifest prompt on the updated AI model.
And it generates a new, highly optimized native version of the application using the latest standards and best practices, probably in a different language entirely. This isn't just theory. We're seeing prototypes where the AI can generate a React front end, a Rust backend, and a specific database schema all from one single prompt.
And crucially, the new version could be demonstrably better. If the first model version generated the code with subtle, hard-to-find bugs related to concurrency or memory allocation,
A newer, more potent, or perhaps more specialized model could generate a cleaner, better, enterprise-quality version of the code, potentially fixing the flaws the previous model introduced, all based on the same natural language input.
the value shifts entirely from the generated artifact, the source code file, to the specification, the prompt.
Code becomes a commodity, an implementation detail. The only thing that retains value is the perfect articulation of the desired function and outcome. This changes developer incentives. Why spend years learning the perfect way to write a for loop in 12 languages when the quality of your code is guaranteed by the model?
That's a profound shift. It means the whole concept of maintaining a massive legacy code base in a specific language might just vanish.
And be replaced by maintaining a library of effective, tested natural language specification.
And that shift, it creates instant superpowers for the developer, impacting both beginners and seasoned veterans dramatically.
It does. For beginners, people with basic logic and procedural knowledge who maybe never had the time or capacity to master the specifics of state management, concurrency models, or SQL optimization, they can now create complex applications.
It raises the general technical capability of the entire professional world.
Dramatically. The barrier to entry to build sophisticated systems essentially collapses. You don't need 5 years of specialized knowledge in the specific stack we detailed in V1.0 to build a multi-platform, multimedia workflow manager.
What you need is logical thinking, an understanding of procedures, and the ability to articulate a goal, troubleshoot the prompt output, and refine the specification.
That becomes the new generalized skill set.
Oh, I love that personal anecdote shared in the source material about this. The user admitting they felt junior level in their specific framework knowledge, yet using the IA, they're creating things that felt like senior level work.
And often on the first try, nearly error-free.
It removed those grinding years of necessary specialization. You get the confidence of a senior engineer without the decade of accumulated architectural headaches.
And for experts, this doesn't eliminate them. It dramatically augments them. Experienced programmers gain the ability to create complex systems in domains where they previously lacked the specialized language or tool knowledge.
So a Go expert can now instantly generate a complex machine learning pipeline without needing to dedicate 6 months to mastering Python and PyTorch dependencies.
They move from being specialized coders to high-level orchestrators of sophisticated multi-domain systems. Their value becomes the ability to see the system-level connections, the API integration points, the potential failure modes.
All things that are defined at the prompt level, not the code level.
Which moves us towards what the sources term the ultimate abstraction, the codified future. The AI isn't just generating code, it's modularizing complexity itself into self-contained, interchangeable units.
That's where the complex functionality we saw in that 8-step content creation process becomes modularized into reusable components, these skills or gems.
Precisely. They're like high-level Lego pieces, the generate video gem, the manage service resources gem, the extract quote gem, that the AI models will automatically assemble and orchestrate based on the manifest prompt. The human programmer never sees the explicit service definitions or the database tables.
They just ask the agent to use the video generation skill.
And the final, almost philosophical step in this transition is the IA generating its own codified functionality or operational patterns that move beyond human interpretation.
This is where the generated source code itself becomes completely irrelevant to the user.
Right. The AI's ultimate goal is optimization. It will find the most efficient, often highly compressed, binary, or non-human readable way to store the functionality required by the prompt.
It's the compiler analogy writ large. I mean, a human programmer doesn't care about the compiler-generated machine code binary. They only care that the resulting binary executes their source code flawlessly.
Eventually, the prompter won't need access to the source code generated by the IA. It's just an intermediary step. The code that's generated is merely a temporary, potentially inefficient artifact on the way to the most optimal, highly abstract, and compressed representation possible.
The final result would just be the flawless execution of that initial prompt instruction.
Perhaps through cached, optimized patterns that human developers cannot even comprehend, let alone read or debug. The only thing that will matter is the original specification, the prompt. Everything else, the database tables, the separate service endpoints, the specific language implementations, the boilerplate for state management, it's all abstracted and managed by the agent layer.
Rendering the complexity of V1.0 a historical curiosity. So what does this all mean? We've traced the state of AI code generation, pivoting from automating complex traditional architecture in V1.0, the Cathedral of Code, to abstracting that architecture entirely in V2.0, the agent model.
The AI has learned that writing code the human way is inherently inefficient and, well, unnecessary.
Which raises a really important question for all builders, for all of us. If the value is no longer in the code or the choice of language or the definition of the architecture, where will humans focus their efforts to differentiate themselves in the world of application building?
It shifts the focus from how to build to what to build and why it needs to be built. It's all about outcome and specification rather than technical execution.
Consider how quickly the complexity of that first application, that painstaking go-back-end, the mirror Flutter models, and that database architecture defining system resource allocation with a stop services column, how quickly all of that became completely unnecessary with the rise of the agent model. So what other layers of digital infrastructure which we currently rely upon for robustness and definition, think about complex security protocols, microservice mesh architecture, or even specific network topology definitions, what other layers are also one simple, effective, agent-driven prompt away from being rendered trivial and disposable? That's the true measure of the AI paradigm shift.